All right, welcome to another podcast. This episode, we're going to be taking a look at an application of multisets. It's actually one of the more important applications we have in counting, as it has a lot of ramifications for real-world applications involving allocations and scheduling and assignment problems and different things like that. The basic problem is we're going to add integers or solve equations where the only thing we can plug in for the equations are integers. So for example, these are actually called Diophantine equations. So if you ever study or run across that word, Diophantine, a Diophantine equation is an equation where you only have integer solutions like this, and it's equal to 15. So it's basically how many different ways can we add three numbers and get 15 if all the numbers have to have certain properties. So you could think of this as having vast real-world applications because you might have certain constraints. For example, you might have three people that need to work a total of 15 hours, and you might have constraints on how many hours those people can work. So for example, if you look down here at problem 3, person 1 can only work 6 hours this week, but person 2 and 3 can work any number of hours, including 0 if they need to. So the question is, how many different work shifts could you possibly come up with that have 15 hours split among those three people? And that's just one small example of the practical application of this kind of mathematics. But the idea is there's many, many different solutions here. And so trying to figure out how many possible solutions there are is kind of a headache if you try to list them. Now, one of the reasons that this is a multiset is just consider the set of solutions. So what does the set of solutions look like for this particular problem? Well, one thing I can come up with here for the set of solutions would be, how about the set 1, 1. So each of these people work 1 hour and then the last person works 13 hours. We normally don't think of that as being a set because we have the element 1 that's repeated. And so this is why they're called multi-sets, because you have elements that are repeated within the set. So that's just one possible solution. Another possible solution might be 0, 10, 5. Another possible solution might be 5, 5, and 5. So you could have three elements repeated, all 5s. But there are many possible solutions, and so our solution set would have many possible items. And so what I want to do is figure out how we can apply this multiset idea to this particular problem. So I think of x1, x2, and x3 as being the bins, kind of like on the marble problem on the previous video, that I can choose to put things into. So each time I put a marble into a bin, that means I'm upping the number x1 by 1. So I can think of it as a counter. I can think of x1, x2, and x3 as a counter, and I want to finish the loop when the counter gets to 15. How many different ways are there to do that if each of these can get split among x1, x2, and x3? So that's sort of a CS example here. And so the idea is basically I have three groups and 15 marbles to place into those groups. And so the answer here is quite simply 3 multi-choose 15, which we know from previous experience is just the binomial coefficient 15 plus 3 minus 1. And I can either choose the stars or the bars. I'll choose since the 3 is smaller here. Actually, I'll choose the 15. Sorry, I'll choose the stars here. And so this ends up being 17 choose 15, which, remembering our formula, 17 choose 15 is the same as 17 times 16, because the 15 factorial cancels, divided by 2, which turns out to be 136. So there are 136 possible solutions to this problem, with all the constraints being that x1, x2, and x3 have to just be greater than or equal to 0. Now if we change it up slightly and say x1 has to have at least one marble in it, then if you remember the marble question, this is very similar. I'm just going to go ahead and place one marble into the bin for x1, meaning I only have 14 marbles left to distribute at that point. And how would I go about doing that particular problem? So if I did that and I only had 14 marbles left to distribute, then that would just be 3 multi-choose 14, which is going to be 14 plus 3 minus 1, choose 14. So this is going to be 16 choose 14, or 16 times 15 divided by 2. So that's 8 times 5, which is 120. Or 8 times 15, which is 120. So there are 120 possible ways to do this. Basically, what we did was we left out all possible ways to have one sort of circulate around. Okay, on to this last one. It's quite a bit more difficult. I want to, instead of counting this, because there's 0, 1, 2, 3, 4, 5, 6 possibilities for x1, so rather than walk through each of those possibilities, I want to count the complement. So if you remember back to a previous video where we did that, we were forming committees and we counted the complement, I'm going to do the same thing here. So what's the complement of this problem? Well, the constraint would be x1 has to be greater than or equal to 7. Since it's integer values, the opposite of less than or equal to 6 is greater than or equal to 7. x2, I still need to be greater than or equal to 0, and x3 has to be greater than or equal to 0, simply because they have to remain positive, so that condition I'm not really negating. I'm not really taking the complement of that condition. So if I solve this problem instead, then basically that's saying x1 has to have 7 marbles in it to begin with, which means instead of distributing 15, I'm only really distributing 8. And so if I'm distributing 8 marbles, this is essentially 3 multi-choose 8, which is 8 plus 3 minus 1, choose 8, which is 10 choose 8. And 10 choose 8 is, let's see here, 10 choose 8 is 45? Yeah, 45. So that doesn't answer our problem. That answers sort of the opposite of our problem, which is x1 having to be bigger than or equal to 7. But the point is, I know that the total number here is 136. So there are a total of 136 solutions, and I'm going to subtract off the 45 solutions where x1 is bigger than or equal to 7. What that leaves is 136 minus 45, or 91 solutions where x1 has to be between 0 and 6. And so my answer for problem 3 is 91. So this is a really important application of counting of multisets, and that is the solving of these Diophantine equations. Now, if you've ever taken the linear algebra class, or the linear algebra, but more importantly the linear programming class here, or the operations research class here, this kind of thing is everywhere in that class, because those classes exist to help you sort of optimize real-world problems based on constraints. And so that's right up the alley of this particular application. And so I just wanted to show you sort of how we can use multisets to help us with counting problems, in particular counting problems framed as Diophantine equations. All right, thank you for watching.